Hello to everyone. This is Srinivasarao Pinchela from the Department of Mathematics and Computing, IIT ISM, Dhanbad. Today we will have an introductory lecture on numerical linear algebra and applications. The contents includes the linear systems, the least square problem, the eigenvalue problem, the generalized and quadratic eigenvalue problem, singular value decomposition, and we also see the computational difficulties arising out of these methods. All of you knowing very well, given an n by n non-singular matrix A and an n vector B, the problem is to find an n vector x such that Ax is equal to B. Does this system will have a solution or not? There are many more practical applications of this system in the real life. Like for instance, you do get in the control systems, you do get in the channel flows, you do get in the seismic waves, you also do get in the some solutions to the linear systems. So essentially the problem is several linear systems with the same matrix A on the left side, which we call it as a coefficient matrix. The problem is to find a matrix X which consists of x1, x2, x3, xn such that the system Ax is equal to B, where the B matrix is B1, B2, B3, Bm is an n by n matrix. So therefore, you need to find out the unknowns X. The unknowns X you need to find out so that you could able to find out the solution to the system. Well, in case of least square problem, given an m by n matrix A and m vector B, the least square problem is to find an n vector X such that the norm of the residual vector, that is norm of Ax minus B with respect to 2 norm, is as small as possible so that you could able to reduce the error. So again, this problem arises in many engineering applications such as signals, image processing, weather prediction, computerized tomography, cloud bursting, and so on and so forth. So therefore, even in statistics also we can find out the least square problem. So essentially we try to trace the parameters A1, A2, A3, An, like A1, A2, A3, like that we have An. So these are n parameters and we try to minimize with respect to these parameters A1, A2, A3, An, etc. will be equivalent to 0. So the necessary condition is dou A1 with respect to the parameter. So it will be 0. Similarly, dou A2 upon dx star 2 will be 0. So like that we do get any equations. So this is the quite often we use in statistics. That is what is called least square problem. The third one which you also do get across in many realistic situations is the eigenvalue problem. Given n by n matrix A, the problem is to find n vectors or n numbers in general, say lambda I, and n vectors xi such that Axi is equal to lambda I xi for every I is equal to 1 to n will have a solution. So here the matrix A is the coefficient matrix, xi is the unknowns and lambda is the scalars. So if you are able to find out the solution to this xi, Axi minus lambda I xi will be 0, then you can find out the what you call the eigenvalues and associated eigenvectors. Typically this arises in the explicit solution of equations and stability analysis of a homogeneous systems of first order differential equations, right? Quite often you do come across the eigenvalue problem also. In fact, one of the example is when you are trying to see the the what you call influence of various parameters for a particular physical experiment. You try to formulate this as an eigenvalue problem with respect to some parameters and see that those parameters how you can be eliminated. For example, you have a optimization problems. The certain function you want to minimize with respect to certain parameters. You may have a one parameter, you have a two parameters, which we call it as Lagrangian multipliers. So that's how we do use what we call the eigenvalue problems. So you can find out several applications in engineering. The fourth one is what we call the generalized and quadratic eigenvalue problem, right? The generalized and quadratic eigenvalue problem. Given the n by n system matrix A, B, C, the problem is to find lambda I and xi such that the equation is lambda I square times of A plus lambda I times of C plus B times of xi is equal to 0 for every I is equal to 1 to n. So here the matrix A, B, C, these are the three matrices, and as I spoke, lambda is a scalar, this is a scalar, right? And you want to find out this xi for every value of I is equal to 1, 2, 3, etc. n. So this is what is called generalized quadratic eigenvalue problem. But a special case of this is nothing but you do have what we call the quadratic eigenvalue problem, right? So what is the quadratic eigen problem? For example, C happens to be zero matrix, that is zero matrix. That means all the entries of the matrix are zero, then the problem is reduced to a generalized eigenvalue problem. So therefore, the generalized eigen problem is much simpler than the usual method, that is lambda I square A plus lambda I C plus B times of xi is equal to 0. Another important decomposition which we come across in image processing, noise removal, in optics, in medical imaging, radiology, and many more areas is the singular value decomposition. How this can be defined? Given an m by n matrix A, the problem is to find unitary matrices, let's say U and V, and a diagonal matrix sigma such that A is equal to U times of sigma V star. So therefore, this is what is called singular value decomposition. That means essentially you want to decompose the matrix A into three different matrices so that you could able to find out a solution to this matrix, right? So that is U is the upper triangular matrix, V is some other matrix, and sigma is the matrix which will have the diagonal elements. So what are the diagonal elements? Whatever eigenvalues you do get, they do lie on the diagonal entries of the matrix, which we call it as sigma. So they typically arises in the explicit solution and stability analysis of a homogeneous system of first order differential equation in the realistic cases. Well, what are the computational difficulties you can see from these methods? There are many more difficulties. So why do you want to go to these very difficult methods instead of going for the regular methods? We will see that what are the problems with the regular methods. Probably if you see, the first one is the Cramer's rule. Large system takes enormous amount of time. For example, if the matrix is A is, let's say Aij 3 by 3, okay, you can able to find out. For the matrix A is, let's say Aij is equal to, let's say 10 by 10. So I can able to find out some way or the other, right? But in general, when the matrix becomes larger and larger, so it becomes very difficult for me to find out the use the Cramer's rule, right? So Cramer's rule, what I do is I wanted to find out the determinant of this matrix, right? Replace the first column by coefficient matrix first column, replace second one and the right side vector B and third vector like this. So it becomes very difficulty to replace every time, and especially when the matrix is very bigger, so it becomes very cumbersome to find out the Cramer's rule, right? So essentially the Cramer's rule is nothing but the determinant of the coefficient matrix upon determinant of this A1. What is this matrix A1? A1 is not a matrix, the elements of matrix A, where the first column is replaced by the vector B. So, which we call it as A1. Similarly, A2 upon the A. Okay, similarly, A3 upon A. So, like that, you keep on doing it, so you get this matrix. So, especially when the matrix becomes very bigger matrix, so it becomes very difficult for us to use this Cramer's rule. So, the other one which you have done it at elementary level is matrix inversion method. Computing inverse is not practical all the time. For example, if you have A is a 3 by 3 matrix, A is a 3 by 3 matrix. So I can able to find out the inverse. For example, Aij is a 10 by 10 matrix. I can find out the inverse of this matrix. How I can find out? So I can find out inverse by using what you call cofactors. So I need to write cofactors. So it becomes very cumbersome to use this cofactors, and it is a very difficult. So if the matrix is large, it becomes very difficult for me to find out a matrix. So obviously the third one is least squares by normal equations. All of you knowing very well in the normal equations, we do setup to find out a least square approximations. So if the matrix M by N has full rank, right? So when do you have a full rank matrix? For example, if you have a matrix of say 10 by 10, right? If you have a matrix of let's say 10 by 10, look at this matrix 10 by 10. Let's say that I start with a matrix A is equal to, let's say, Aij 10 by 10 matrix. So what I wanted to do is, I wanted to set up a normal equations. So if the M by N matrix A has full rank, that means the number of linear independent rows or columns, okay, will determine the full rank, and M is greater than or equal to N, then the least square problem has a unique solution, and this solution is theoretically given by the solution X to the linear system A transpose, that is A transpose Ax is equal to A transpose into B. So this is how you do get a solution. So these equations are known as normal equations, having difficulty for sensitivity to perturbation, and they corrupts the accuracy. Therefore, there is a difficulty for using these systems. Well, now when it comes to the computing the eigenvalues by characteristic polynomials, is not a suitable approach because round of errors blow up. So all that what you do is you want to reduce the error check, wanted to reduce. Okay, so how do you reduce this error? And there are many ways of reducing the error, solving the generalized eigenvalues. Say that Ax is equal to mbx, right? So you have Ax is equal to m times of bx. Assume that these matrices are commutative, so I pre-multiply this matrix with B inverse of Ax is equal to B inverse of mbx, and that can be written as m times, that can be written as, that is the I, that is, so I times of B inverse of Ax, so therefore you do get as B inverse of x, which is nothing but B inverse of x, A is nothing but x, m, capital M. So computing inverse is a costly affair. So all that what it happens is finding out the inverse of this matrix. Inverse is a costly affair. So therefore it is not desirable to use the inverse of the matrices over when the matrix is, especially when the large size. So essentially the size of the matrix also very important. The methods which work for small size may not be desirable for the system is bigger systems. Now let's look at into the numerical methods. How do you find out the norm of this matrix axis? Norm will give you the stability and other properties of the matrices. So if norm of infinity norm is nothing but maximum of 1 less than or equal to I less than or equal to n, that is for every x belongs to Rn. That is what is called infinity norm. Similarly, you can write the 2 norm. norm of x2 is equal to x1 square, x2 square, xn square, which belongs to set of the real numbers Rn. So, well, you can see some example over here. So, for example, you have given a matrix A is equal to 1 minus 1 3 2 and x is equal to 1 2, y is equal to ax. That is, the system is, if you look at 1 2 is 2 minus 1 minus 1, 3 1 is 3, 2 2 is 4, 7. So, therefore, ax will be 7 minus 1 7, which is the matrix A. So, if you want to write the norm of A infinity, which is nothing but maximum of I lies between 1 to 2, and maximum summation I is equal to 1 to 2. So, you get that. So, that is similarly you get the infinity norm. So, if you take the infinity norm of A matrix, it is 5, infinity of Y will be equivalent to 7. So, this will give you the characterization. So, this will give you characterization of matrices. Well, now let us look at another example. In base 2, the numbers are 0 and 1. As an example of the conversion of a number to decimals, so we use this strategy. Look at here. So 1, 2, 3, 4, 5, 5 digits. So you do get a 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So that means including this dot you get a 7. So therefore you can able to find out the how you can convert it. This is the number which you get it when you transform it to binary to decimals. This is the decimal way of computing. Well, let's look at into the another example. For example, if you are looking at into base 16, the digits are 0, 1, 2, etc., 9 and A, B, C, D, E, F. So you see that how actually 56 EF is 16, base 16 is converted into the decimals. That is, you get 1388.9375. So when you are doing this, you do use what you call rounding, similarly chopping. Rounding and chopping. Let's see how it affects the system. So if you do rounding, what is the problem? If you do chopping, what is the problem? And what are the instances to carry out the chopping and rounding? And the one of the important issue is numerical analysis, stability analysis. A number of mathematical problems have solutions that are quite sensitive to small computation errors. For example, rounding errors. To deal with the concept of stability and the condition number, so this condition number of a problem will closely related to the maximum accuracy that can be obtained in the solution. So that means stable solution is which we also call it as well posed. So when you are saying that it is a stable solution, which we call it as well posed, and when the problem is unstable, which we call it as ill posed problems. So trying to find out a solution to the ill posed problem is very typical task, and well posed is quite easy. We can able to find out the solution to those things. Well, so let's see that stable one example. If the solution x depends in a continuous way on the variable y is equal to fx, then it is stable, else it is a unstable. And what are the stable problems? Examples: ax square bx plus c are say not equal to 0. Any solution x is completely number x is equal to minus b plus or minus b square minus 4ac by 2a. The two solutions for x will vary in continuous way with the data y is equal to abc. Let's see another example for the unstable problems. You have unstable problem that is 0 to 1. Let's say that 0.75 xt upon 1.25 minus cos of 2a times of s plus t is equal to ys. So where s lies between 0 to 1. So this is unstable problem. These are perturbations. Sn is equal to yns minus ys, and we write it as maximum of s0 to 1 mod of Sn of s tends to 0 as n tends to infinity. So these are called unstable problems. So unstable problems are difficult to solve. Unstable problems are difficult to solve. Well, if the problem is unstable, there are serious difficulties in attempting to solve it, as already we spoke it. It is usually not possible to solve such problems without first attempting to understand but about the properties of the solution. So the condition number attempts, in fact, condition number can define in the many possible ways. One of the ways, the way which many people are using in the what you call the fuzzy logic systems, right? There also we use the system is stable or unstable. The condition number is it attempts to measure the worst possible effect of the solution x f x y is equal to 0 when the variable is perturbed by a small amount. So in realistic situations, the perturbation is quite often because you need to handle the realistic situations. You see the stable system, how it looks like. So you have a stable for small n and unstable for large n. So when the matrix size becoming larger and larger, the methods which works for stable may not exactly work for unstable. So therefore, very difficult to solve these unstable problems. So the inverse y equivalently solving yx is equal to I is well posed. The solution x can be obtained by a finite number of steps using single arithmetic operations, but the problem of calculating x is increasing ill conditioned as n increases. That means when n becomes bigger and bigger, so when n becomes the bigger and bigger, that is infinity means bigger number. So therefore, this is actually the decreases. That is what is the idea of ill conditioned, well conditioned. Let's say that one method, secant method. Secant method is not guaranteed by convergence. So quite often method, what we do is we try to, in order to find out the optimum method, we tend to make into the small pieces. Then we do see that whether the small pieces converges or not. Secant method is not guaranteed for convergence, but when it does converge, the speed of the method is greater than the bisection method. So what you do is, in the case you bisect it and try to see the subinterval, smallest subinterval where the root lies. Similarly, another method is what we call Newton's method. Newton's method requires function evolutions or iteration value. So the Newton's method, it requires two functional values. That is, you need to find out the value of the function fx as well as the derivative of the function fx. So therefore, finding out the derivative is very tedious. And second thing is, if the denominator happens to be 0, that is f prime, then we will not be able to apply the Newton's method. So there are some the limitations for this. Other one is the Newton method is converges more rapidly. In fact, the solution it converges more quickly. Consequently, it will require fewer iterations, small iterations, so that you will be able to get the desired accuracy of the solution. That is the background of the Newton's method. So, in all that, you do see that Newton's method is quite effective despite of having so many the hurdles. The other one is what is called the Muller method. For obtaining both real and complex roots of a function, it is a generalization of the approach that lead to the secant method, right? That is what is called Muller method. And the function fx has a root alpha, say p, then p is greater than or equal to 1. So if p is equal to 1, so if p is equal to some other, then it doesn't belongs to those values. So therefore, numerical evaluation of multiple roots also very difficult in order to find out a solution. Okay, you may have a multiplicity. Simple multiplicity is 1. So in that case, not much difference could be seen in the case of simple multiplicity. Well, what is the Muller method is? It is if fx is sufficiently large and differentiable at x is equal to alpha, then this is equivalent to, we can write it as f alpha, f prime alpha, all those things will 0, but pth derivative would be free from 0. Okay, then we can apply the Muller method. See that simple example. If you have a f1 is equal to x square minus 3 and f2 is equal to 9 plus x square times of x square minus 6, then alpha is equal to root 3. So they as multiplicity 1 as a root of f1 and multiplicity was 2 as a root of f2, because there is a difference between f1 and f2. F2 is actually the x square minus 6. So therefore, when x is equal to 6, it always directly lies on the scale, where the first one is not being in the scale, because when you substitute it, it won't get vanish. Well, so I gave a very introductory lecture today, and I'm sure that it's an introductory lecture, and please go through all the definitions, and in the next lecture we would try to see that what are the difficulties with the computational methods, and what is accuracy, what is the order of magnitude of dimension analysis, and how these things could be handled in a very special cases. So that makes the first the complete chapter 1, which will give you the introduction to the numerical methods and also introduction to the numerical linear algebra, and together which we call it as numerical linear algebra, and having some engineering applications. So that's how we do justify that the course is very useful for the especially engineering graduates and other people. Thank you very much.